right, so today we're going to be going over chapter 19 about free energy thermodynamics. There's a lot to go over. We're going to learn about all three laws of thermodynamics and going into a bit of detail about energy transfer and a lot of cool stuff. So we kind of started a little bit 2 weeks ago, but just to refresh your memory, the first law of thermodynamics, this is my favorite law because it's the reason why I'm not afraid of zombies. Growing up, I was really afraid of zombies and afraid of really any like horror movie kind of scenario, like A Quiet Place, right? That was a great, well, that was a recent horror movie. That's a really good horror movie, but it follows the same law, thermodynamics, the first one. So basically the first law of thermodynamics states that energy cannot be created or destroyed. What that means is that if you have like an alien creature from A Quiet Place, eventually, if there are no more people, if you just hide, it will die because it will run out of things to eat and it cannot consume any more energy and it will die. Same with zombies. So Dawn of the Dead, where that's kind of comedic, but like they're supposed to be serious, but they were in the mall and they locked themselves in the mall and there were zombies everywhere. What will happen in real life is the zombies would either eat each other or they would just die of starvation. Because if you just lock yourself in the mall with Cheetos, you can live for a few weeks and then you will live and then they will all die. So, or they'll be so slow and incapacitated that you can just easily walk past them. And Sumi's question, but they have plenty of humans. Debatable. I mean, depends what your setting is. I mean, the point is after they eat everyone, like I Am Legend, great example, one of my favorite movies of all time, doesn't obey the first law of thermodynamics because all those zombies that are running really, really fast, that are muscular, that have all this energy, where are they getting this energy from? There's like 2 animals in the whole city and they hunt them. And by the time Manhattan's a closed off island and he's been there for 3 years or so. So by that time, the amount of edible food would run out for the zombies and they would die. Well, I'm afraid of zombies in real life. So not the movie. The movies are interesting because as a chemistry professor, I'm thinking about the first law of thermodynamics all the time. And that makes me feel better about them. But anyway, let's continue. So the second law of thermodynamics has to do with, okay, where would I hide? In what, a mall? Anywhere with food, honestly. Anywhere with food. Because you gotta have food. I would make certain stops though. I'd go to like the sports section, get some weapons, or if they have like depends what mall it is too. It depends what kind of store they have. The stores they have. So anyway, might go to get some nice clothes. Who knows? All right. So second law of thermodynamics. It has to do with the dissipation of energy into the surroundings. And what we mean by this is there's this thing called entropy, which is the main idea of today's lesson, which is a new thing that we're bringing to energy. And entropy is the definition of it is just the disorderedness of the particles in the universe or in a specific area, either in the system or in the universe. And the second law, it states that the tendency for energy to spread out is due to the energy tax, meaning the loss of energy that in a transfer of heat or any type of energy from one substance to another. There's always a loss of energy. You can never transmit 100% of the energy from one thing to another. That means from the air to the ice when ice is melting. That's one example. And also like hot coffee to the cup, things like that. So there is always a loss of energy. And this loss of energy increases the entropy of the environment, of the universe, meaning it increases the disorder of the molecules in the universe. So has the second law of thermodynamics, and it ties very closely to, okay, we have too many questions. All right, hold on. So even in a vacuum, yes, even in a vacuum. And resistance in a wire, sure, I guess so. And food pyramid, exactly, yes. All right. So guys, also if you have questions, most of you should all have microphones, so you can feel free to say professor and say a question, because otherwise I have to go back and look at the chat every time. So Okay, so next we're going to talk about spontaneity. So spontaneous, or if something is spontaneous or not, is very relevant to the second law, and it's very relevant to entropy. So spontaneous, what that means is that without any outside energy, that a reaction will occur, an energy transfer will occur. So the chemistry example that I can give, I'll give a chemistry example, then I'll give a water example. For something that's spontaneous, if you have two lone hydrogen atoms, as we saw from the energy diagram from chapter, I think, 11. Oh, let me draw here. So hydrogen atoms are normally at a higher energy state by themselves, but when, this is the energy curve, so they come from this level of energy, this level of energy, but when they bond covalently, the H2 molecule is at a lot lower energy than each hydrogen by itself. And this is due to the stability of the covalent bond. And this is why a lot of our inert gases and a lot of our diatomic gases are the most prevalent form rather than the elemental form, is because they're the most energetically favorable. And I've said that term a lot in our class. And if you had me last semester, energetically favorable. What that means is it means spontaneous. So, and also we learned where we went over the bonding orbitals, right? The molecular orbital diagram, where you have, or sorry, there's one electron for hydrogen. We have the one electron, then you have the bonding electrons, right? So the bonding electrons, they would all be down here at a lower energy state. And that's why we have the different levels, because there's a spontaneity to this. And there's a high likelihood that it will happen because the covalent bond is at a lower energy level than each of the hydrogen atoms on their own. And that's why the bond order of this is going to be 1 rather than 0 being unfavorable, or negative being unfavorable. Well, it's not possible to be negative. If it's 0, it's unfavorable. Okay. So the other example I can give is ice. So at room temperature, ice turning to water is a spontaneous process, meaning there's no external energy that's being applied for it to happen in room temperature. So keep in mind, obviously, if you're at a colder temperature, ice will be ice. But in that case, and if you have ice going to water, and we'll talk about this example later, but the water molecules are actually increasing in energy. It's an endothermic reaction. The disorder of the water molecules and the movement is increasing, but it still is spontaneous. So you can start to think to yourself, how is a process going to gain energy, but it'll still happen spontaneously? And we'll answer that question in a bit. And that's unlike the hydrogen example, where clearly when these bond together, the whole process releases energy. And all this energy from the individual hydrogen atoms is released into the environment, into the surroundings. And also, spontaneity doesn't really mean slow or fast. It just means it happens. There could be non-spontaneous reactions that are faster than spontaneous. But again, it's very reaction specific. So here's an example, other examples of spontaneity. So if you have simple mechanical potential energy, where if you lift something up with a pulley, there is mechanical potential energy in that object, mgh, right, from physics, and the direction of its spontaneous change is down. So if you release it, if you add no more energy to this, so you need energy to hold it in the same spot, but if you have no energy input to the system, it will fall down. Same with solid NaCl. If you dissolve NaCl, it will spontaneously dissolve. The Na and the Cl will dissociate from one another because that is the energetically most favorable ionic positioning of them, meaning the water molecules will rip the NaCl apart into its charges, as we talked about, or as you learned previously. Okay, so other examples are diamond to graphite. So spontaneous process can also mean a more rigid and tightly packed structure to a looser, less energetic structure. So what I mean by energetic structure is sometimes bonds are very close together, and that forms kind of like an increase in energy, basically, because there's atoms that have their electron clouds so close together that it creates a repulsion effect. But graphite is at its kind of happy level or happy distance in the bonds and the covalent lattice of the carbon atoms, whereas diamond is a little bit too dense. So over time, very, very slow, over millions of years, then the diamond actually turns to graphite. So don't sell your diamond, though. I mean, it's still going to be good for your lifetime. And it's such an indiscernible amount, even over hundreds of years, that it doesn't matter. Okay, so we're going to be learning about not kinetics. We already learned about kinetics. And now we're going to be focusing or shifting our focus to thermodynamics. Now, the difference is kinetics, we were talking about the rates, the speed of the process, and exactly what was going on there. But now we just talk about the end and the beginning. So what we're going to do in a big skill of anything having to do with energy in a chemical reaction is we're going to compare the states of energy of the products and the reactants. So usually the delta energy, the change in energy, will be the sum of the product's energy minus the sum of the reactant's energy. So that's the case for a lot of and when we learn about Gibbs free energy, that will also be the case. Okay. So again, with a spontaneous process, most of these spontaneous processes are like the first one that I mentioned with the hydrogen gas formation. Same with oxygen gas, same with nitrogen gas, where you have high energetic particles that are bonding to be in a more energetically favorable position at a lower energy. And that energy that is lost from the lone atoms is now being dissipated into the surroundings. And obviously we know this is called exothermic, an energy release. So that makes sense that most of them are spontaneous because the energy goes from in the molecules to the surroundings. But some of our spontaneous processes, like the melting of ice to water, is actually endothermic. Are there any questions there? I heard a microphone. No? Okay. All right, so it's actually endothermic. So the question is, that I asked before, is how can something just spontaneously absorb energy? How the hell does that make sense? But also release energy into the environment. That makes even less sense. And the answer is entropy. So here's the idea of melting of ice, is that what is actually happening when ice is melting is the energy from the room temperature environment, or anything really above 0 degrees Celsius, is spontaneously changing the crystal lattice of ice into liquid water. The energy going into that liquid water also increases the entropy of the water, meaning the system, of the water, becomes more random. So the movement of the water molecules, where before, if you look at these diagrams, ice is a crystal lattice here. But when you melt ice, it now becomes a disordered liquid, meaning there's more macrostates and microstates, basically meaning more positions. And we'll learn about macro and microstates in a minute, but it basically means there's a lot of movement. So more movement, more entropy, more spontaneous. That's very basic. And that's a good thing to know. So entropy equals spontaneous. If entropy is positive, meaning a gain in entropy of the universe, then it's a spontaneous process. Okay, so water evaporating is another one. Same kind of concept, but we're going from a liquid to a gas, where clearly even though you're increasing the amount of energy that are in the molecules, their spontaneity increases, which means that the entropy increases. Same with salt dissolving in water. Talked about that one already. Now, this gets to the second law, which we talked about before, but a more concrete definition is that for any spontaneous process, the entropy of the universe is positive, greater than 0.
Professor?
Yes.
Wouldn't you say that like spontaneity is like directly proportionate to entropy? Like the more spontaneous something is, the higher the entropy is?
Of course, definitely. Good, yeah, that's exactly right. So yeah, so entropy, we use the letter S for entropy. maybe S for second law. I don't know. That's the way I remember it. But S is for entropy. And delta S is change in entropy. So basically, it increases with the number of energetically equivalent ways to arrange something. So what that means is the amount of disorder in the substance. And it's a state function, meaning only the final and the initial values matter. So you can do final minus initial, and you get delta S. And these could be really simple problems given to you, but there are also other equations that we're going to learn about that you can actually solve for S. And that involves Gibbs free energy and other equations too. And here's one of them that you may need to use on the homework, but it's one of these simple plug and chug equations. So here is that equation. We have S equals K natural log of W. Now, what we can say is that K is our Boltzmann constant, which is joules per Kelvin, and W is a kind of a weird number. It's the number of energetically equivalent ways that the molecules exist. So that's a weird thing to say. If you have a mole of molecules, well, not even a mole, if you have 50 molecules, the amount of arrangements that they can make and still be energetically equivalent is huge, 10 to the 20 something. So that number is going to be very large. And if you imagine for entropy, so if you figure it here, if entropy has to be a number in joules that is relatively like scalable. So it's like, let's say we have, could be 2,000 joules, right? It could be 20,000 joules, but it's a number that it's not 10 to the 15th. So what that means is that K, which is our Boltzmann constant, needs to be kind of canceled out by our natural log of W. That means natural log of W has to be on the order of 10 to the 20 to 10 to the 25th-ish, in that range, in order for it to kind of cancel out with this, with the Boltzmann constant. So if the natural log has to be that much, and remember, a natural log curve goes like this. So if the natural log has to be that much, that means the number itself has to be 10 to the 30, 10 to the 40 of W. And that's usually true for if you have moles and moles of substance. So these numbers are going to be pretty large. So just keep that in mind. Does it really mean much, the W? Not really. I mean, it's just the number of ways. And you might have to solve for that, or it might be given. But again, the only ways you will see this equation given on in a homework or exam will be a plug and chug, basically knowing two of the unknowns and maybe calculating, or knowing two of the variables, calculating the third. Okay, so then we can, this W, this number of possible arrangements of particles, can be defined into macro and micro states. This is what we use to explain it. Now, we're going to explain it on a very small scale, meaning only 2 molecules, maybe 4. But once you get higher than that, it gets exponentially crazy. But a macro state, we'll talk about macro state first, it's the easy one, is the state defined by the setting, the environment, the parameters of the container, meaning the pressure, the volume, and the temperature. So if you put one beaker, or if you have a beaker, and you look at and you're the perspective of any single water molecule in that beaker, you will all have the same macro state. Meaning, okay, you're all under the same pressure, you're all in the same volume, you're all under the same temperature. That's just the state of the system overall. The microstate is the exact, in their definition, the exact internal energy distribution among the particles at any instant. What that means is if you're a particle in a beaker of water, you're looking at how fast am I going compared to the water molecule next to me. I'm one microstate, that water molecule's speed is another microstate. And the one that's bumping against the side of the container is another microstate. And you can imagine with gases, it gets crazy. Because if you remember the distribution of kinetic energy or the velocity of gases, they normally look like this, the distributions, where most of them are, it's usually like a normal distribution almost. But it's a Gaussian curve. But anyway, so you have most of the molecules are around the same speed, and the average is here. But you have billions and billions of molecules that are at the extremes. at the extreme slow and extreme fast. So the sum of all of these different possibilities is W. So imagine that number is freaking huge. Okay, so let's take a look at micro. Are there any questions on that? First off. No?
Can you explain microstates again?
Sure. So I'm glad that you mentioned that. We're going to go right into explaining more about it. So good that you mentioned that. Okay. So here is an example of microstates. It is, think about the perspective of the particle. And for those of you who are engineering majors, it may not make sense. So, okay, you have system A, right? You have the blue and you have the red. Let's say they're electrons and they're at energy level 2. They're identical. They're identical particles. They're electrons. Energy level 2 joules. All right. One of them will go here. The other one will go here. One of them is at 3. One of them is at 1. The macro state of that is, all right, one's at 3, one's at 1. The micro state is the red one is at 3, the blue one is at 1. Whereas for system B, which is the second microstate, or they're both system B, but the second microstate of system B is the blue one is now at 3 and the red one is now at 1. To the microstate, or sorry, to the macro state viewer, they're the same exact thing, right? Because, oh, you have one of the particles at 3, one of the particles at 1. But if you're looking at the microstate of exactly this identity of particle, if you gave all the numbers, particle 1 and particle 2, you're going to have 2 here and 1 here. Here you have 1 here and 2 here. They're clearly different. So that's what we mean by microstates, is the number of individual arrangements of the particles in the system. Yes, exactly. So Sumi, that's a great example. So if you're flipping 3 coins, it could end in 6 ways, right? Because you either have 1 heads, 2 tail, whatever, all the different ways. 3 factorial, right? 3 times 2 times 1. But if you're going on the microstates, there's a ton more because you're basing it off of which coin lands on heads, tails, or whatever. So you gave them all a number and then did it again, you'll get a ton more. So we'll show you another example. Here we go. So we have macrostates, macro to micro. All right. So you have particles. There's 4 particles in these. These are gas particles in like a tube with 2 flasks. We can call these 1, 2, 3, 4. The macro state is there are 2 of them on the left, 2 of them in the right. But the point is, like Sumi was saying, which 2 are they? So if we numbered them, let's say they were, I don't know, ping pong balls or something, and we numbered them, 1, 2, 3, 4, we would actually come up with 6 different microstates because you can have 1 and 2 here, 2 and 3, the different combinations that can possibly be observed of each individual particle. Okay, any questions on that now? No? Okay. All right. So now we can talk about why does that matter? The reason why that matters is because we can tell based on how many microstates there are, or not the exact number, because we'll never know the exact number, but the likelihood of one happening versus the other. And we can tell which one's more possible or not, or which one's energetically favorable. So let's take the same example where we have those 4 balls, 1, 2, 3, 4. And they're in state A, state B, and state C. So these are all different macro states, right? You have 4 here, 2 here, 2 here, right? There's 3 different macro states. How many microstates are there in A? And let's just consider, okay, so don't consider the actual positioning of them. So like, don't be like, oh, one can be here, 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 or here. Just say left or right. How many different macrostates are there for A? 2. Well, Okay, so Sebastian, why do you think there's two? Okay, so we're talking about state A. So why do you think that there's two macrostates? Sorry, two macrostates for this.
Oh, I might have been.
Or sorry, microstates. My bad.
I might have been thinking about this wrong. Like if they're either left or right, then.
Oh, that's exactly it. Okay, so you're correct there. But let's just say if they were all on the left, like in state A, how many macrostates is that?
One.
One, right. And so then how many microstates will it be also?
Oh, just for the left. Oh, then it's one. Yeah.
Exactly. Then it's also one, right? Because if you consider the only options are left and right, if the macrostate is they're all on the left, then the microstate is they're also all on the left.
Right, because it doesn't matter like top corner, bottom.
It doesn't matter. Yeah, it doesn't matter if top corner left. Let's say in reality it does, but we'll see what happens even if it does. So yeah, let's just say it doesn't right now. Then for state B, same thing, meaning this is the macrostate and there's only one microstate, is they're all on the right. But for state C, there's a difference. So you don't have to tell me how many we just saw how many microstates there were. But now for this one macrostate of two on the left, two on the right, the question will be which two? You can't ask that question with A and B. You have four on the left. Which four? Well, all four. You have four on the right. Which four? All four. But here you have to say which two, because it could be 1 and 4, 1 and 2, 1 and 3, and so forth. So then you could even say, you can go a step further and be like, all right, professor, what if you're thinking about the top left, bottom right, top left, whatever. So if this was macrostate A and they were forced to be on the left, you can say, all right, there's a ton of them. One could be in top left, bottom right, top whatever, right? But if you look at state C, that makes that's another variable that also increases state C's microstates by a lot more. Because for these two molecules, you can now say which two, and you can say which position are they in. So even if you factor that in, you'll still have a lot more microstates for state C. And yes, it's like using permutations and combinations kind of thing. Oh, I hate stats, or I hate the traditional class of stats. I like statistics, but I don't like the class. Yes, yuck is correct. Okay, so let's move on from here. And we saw that. So now here's what basically what I just explained. There are 6 times the probability of having state C than either state A or B. So if in reality, because you have the different microstates in one macrostate, you have 6 microstates in state C, and you have 1 in A and 1 in B. That means C is 6 times as more likely as A or B. And we can see that there. So then we can ask a question. So consider these 3 changes in possible distribution of 6 gaseous particles. Which one, and also keep in mind, the more microstates you have, the more your entropy is. Because the more arrangements you can have. That means the larger freedom of your arrangements. That's why we're learning this in the first place, is we're relating it back to entropy. So now knowing that, which of these different distributions, now gives the largest, or has a positive change in entropy? And good, Sebastian. The answer is N-mod. Good. So the answer is A. Right, because this transition, now you're giving, here you had maybe, I don't know how many, but then when you split them apart into our different 2 in each chamber, you then maximize the amount of microstates you can have, meaning it increases the amount of positions definitely compared to B, and also even compared to C, because you're taking off one box. So what that means is, in this case scenario, you have the largest amount of entropy, if you want to take it a step further. So the more microstates, the more entropy you have. Good. Okay, so we talked about this already. So basically saying that the entropy or the macrostates and also microstates, meaning the more energy you have. So as you increase, when I say increase your physical state, I mean increase the degrees of freedom or the entropy of your molecules going from solid to liquid to gas. Then you increase your entropy. So, and that should make sense based on what we just learned with our micro and macro states. Exactly. So Sumi, the basic idea is more disorder and more movement of the molecules equals more entropy. And it could be kind of common sense because based on what we learned and what we know about solids, liquids, and gases. So more, that's a good thing. I'm going to write that down. More disorder equals higher entropy. Good. And that disorder increases from solid to liquid to gas. Okay, so now we can go a little bit, we can kind of reverse our thinking a little bit. We can say that we know the second law demands that the entropy of the universe increases for anything spontaneous. But look at the example we just went over. When water vapor condenses from liquid to, or sorry, from gas to liquid, the entropy, it's spontaneous, but the entropy is decreasing for the molecules of the water themselves. Why is that? So that's basically the third bullet point. It's spontaneous, but the entropy is unfavorable for the system. The only way that's possible is there must have been a large increase of entropy to the surroundings. So if you look at the fourth bullet point, you could say, all right, if that's the case, if my energy from the material was now released into the surroundings and enough to increase the entropy of the surroundings, it had to be exothermic, has to be. So if the entropy decreases and it's still spontaneous, it has to be exothermic. All right, I know I said a lot of things, a lot of terms right there, but ask questions. You can say, what do you guys think? Let's hear you. Or read. I can read too. You're still processing it? All right, so I'll say it again. Try to say it differently. All right. So the original claim was that if you have an increasing entropy, or if you have something that's spontaneous, that means the entropy of it increases. The entropy increases. And the second law of thermodynamics was the entropy of the universe increases. Totally true. But you can imagine, all right, if it's spontaneous, shouldn't the entropy of the stuff increase, the system? Not necessarily. For example, water vapor condensing into liquid. So, Sumi, not all the time. That is only true. So if you were looking at the comments, so you said that universe entropy increasing means the system decreases. That is not true because the system is part of the universe. So something that we should understand before we continue is system plus, I'll put for surroundings equals universe. So if that's the case, and the universe, for any spontaneous reaction, it is given that S increases, meaning entropy. The system might decrease. For example, water vapor condensing to liquid. It's spontaneous, but the entropy of the molecules themselves, because they're going to a lower state, increases. The only possibility for this is what? In this equation, what is the only possibility to make this work? Good, SIR goes up, exactly. The surroundings entropy has to go up a lot. So that makes perfect sense. And what does that mean? If the surroundings entropy goes up, the energy to make that surroundings increase has to come from the system, which brings us to our conclusion that it has to be exothermic. Okay, good. All right, any questions on that? No? Okay. So you can rewind this part of the video and hear that explanation again. I think I did a good job explaining it. But of course, you can ask questions later on. Okay, so here's a graphical representation. So let's say you have, this is water condensing. So you can see that the entropy of the system's losing entropy. But the surroundings gain the entropy that it's a little bit more than what the system loses. And if you add those together, you get a small increase in entropy of the universe. This means it's favorable. Things could be unfavorable if this delta S of the universe, or if the system loses more entropy than the surroundings gain. That means the energy had to come from somewhere else. That means the surroundings pushed in more energy to the system, meaning it's not spontaneous, and delta S would decrease. And here's an example of that. So if you have, question. Oh, so that, right. So where's that little bit of extra entropy in the surroundings come from? You know, so you mean here, like, why is this a little bit larger than this?
Yeah, I'm essentially asking the same question that Sebastian just asked. That like, doesn't entropy follow the law of conservation of energy? Or
so entropy is not energy. It measures disorder.
Okay.
So what happens is if you release a little bit of energy, it could onto a lot of particles. It creates more entropy than if you released it onto a smaller amount of particles. So for like the surroundings always has more particles than the system. Meaning if the system releases energy, there's going to be more particles affected that are going to increase their entropy in the surroundings, making the entropy of the surroundings a little bit larger. Okay, cool. Good, very good question. Very, very good. Okay. So when you have a system's exothermal, we can be talking about that, increase the entropy of the surroundings. So it's about temperature. So temperature, I mean, so when water freezes below 0 degrees, it happens spontaneously because there's heat that is released from the water in order to warm up the surroundings, meaning increase the entropy of the surroundings. And it will increase the entropy of the surroundings more than the entropy lost from the ice, because there's more molecules in the surroundings. So that's why delta S would be positive, even when we have melting of ice going to a less entropic system state. And then we can throw more equations at you. So if you want to quantify the heat, so let's say in a perfect transfer, you have the heat of the system that is lost equals the heat of the surroundings that is gained. And you can come up with this equation at a constant pressure and constant temperature about the change of entropy of the surroundings. There's a big derivation, but I skipped the derivations. That's beyond the scope of the class. But you can come up with that the change of entropy of the surroundings equals negative the enthalpy's back, right? Enthalpy of the system, that's the heat of reaction divided by temperature. Okay, so yeah, and of course, all these equations, if they're going to be used, will be given on exams, on the final exam. Okay, so here we go. So by absorbing energy from their surroundings and synthesizing large complex biological molecules, plants and animals tend to concentrate energy and not disperse it. How can this happen? So you perceive to create energy and concentrate it, right? So what is the only way that spontaneous, and I mean, like, these biological things are pretty spontaneous. I mean, some of them are, like diffusion, for example, is spontaneous, or yeah. But anyway, so biological systems only appear to concentrate energy. In reality, large complex molecules have more entropy than the substances from which they are composed. I mean, I'll let you guys think about that. What do you guys think? So we have a B question mark, and B question mark, Ahmad, is the answer. And Sebastian, good job. So B is the answer. Now, A doesn't really make much sense. It's kind of confusing. What they're trying to say is, let me read it. So biological systems only appear to concentrate energy. In reality, the molecules have more entropy than the substances of which they're composed. That's not true because they're composed of smaller substances. And if you have like a protein, for example, it has less entropy than the components that it's made up of, the amino acids. Each amino acid on its own has more entropy than a protein. Protein is, even though it's gelatinous, it's still more of a rigid structure than the summation of all of the free amino acids in the solution. So that's not true. And then B is true because the biological systems, they decrease their own entropy by creating more entropy in their surroundings. That's how molecules are formed. That's how biological molecules are formed, like a protein. So, okay, so how do they do that? Good question. Now, let me think. So proteins are made from, we'll use a protein example because I'm a protein biochemist. So proteins are made from amino acids, right? And you have a whole big process on protein synthesis. Now, that whole process requires energy. It requires ATP. ATP, when it is broken down and into ADP, the phosphate's released. The phosphate is charged. And this is one molecule, although there are other molecules that are also released in this process, and there's a lot of molecules that are moving around. So basically what we're saying is, in order to make a big machine, there's a lot of little workers. So all those little workers are creating more energy in their surroundings in order to make the big machine, meaning the protein. That's in layman's terms of what's happening. But you have the transfer RNA, you have the messenger RNA, and the messenger RNA is moving from the nucleus. That's a lot of energy. That's a lot of entropy increase in the nuclear membrane. The nuclear membrane has to open up, and the pores of the nucleus, nuclear pore complex, has to release the messenger RNA. That's a lot of entropy increase there in the surrounding molecules and channels. And then you have an attachment to the transfer RNA, which then brings it to the ribosome, which is a lot of other mechanical processes are going on there. So it is insane. So basically you have a lot of smaller molecules that are creating a lot more heat and energy in their surroundings in order to synthesize this one large biomolecule called a protein. Even though the protein itself has a lower entropy level because it's more rigid than the little tiny components. So yeah, that's nuts. That's why I'm a biologist. It's really cool. But my research is not about entropy on biomolecules. So I'm not the expert in that. So anyone on YouTube listening to this video and who is an expert, and like, well, technically this is whatever, probably, but I mean, I'm not an expert on that specific field. Okay, so let's move on to other important things. We have Gibbs free energy. So Gibbs free energy, what it is, it's, let's just, in terms of definition, the chemical potential energy. Chemical potential. So whereas the enthalpy, H, which we learned about, is the heat energy generated from a chemical reaction. The delta G is now the potential energy generated from it. So it's, yeah, it includes the enthalpy, but you also have to subtract the heat now. And that's called the heat factor, which is the temperature times the entropy. So if you don't want to go through that process of understanding it too much, but here's the equation and you need to know it, or you need to well, it's good to know it, but it will be given, I think, as well on the final exam. So delta G equals delta H minus T delta S. And keep in mind, even though it says system here, system and system, that's important because the entire Gibbs free energy equation has to be either for the system or for the surroundings. Either one's possible. H is enthalpy. H is your enthalpy. And Luke, you spelled it wrong, but it's okay. I spelled it. Oh, it's an O and a P, whatever. It's okay. All right. So, yeah, enthalpy. Good. So, a rule with delta G about spontaneity. When delta G is negative, the reaction is spontaneous. Very good thing to know. So you can tell immediately from a delta G value, is it spontaneous or not spontaneous? Just like you can tell from a delta H value, is it endothermic or is it exothermic? So keep in mind, so this equation is very powerful. What it's doing is we're taking into account the exothermic or endothermic nature of a reaction. And we are combining that with the entropic value, whether the system gains or loses entropy. And based on both of those things, is the reaction spontaneous or not? Because we learned in some cases, when the entropy of the system increases, meaning when ice becomes water, it's spontaneous. But sometimes when the entropy of the system increases, or well, let's use this as a better example. Well, yes, well, but when sometimes, but we know, hold on, let me try to get this right. So we know when ice goes to liquid water, the entropy of the system increases. But we also know, and that's spontaneous, but we also know when lone hydrogen atoms become an H2 molecule, the entropy of that system decreases, yet they're both spontaneous. So this equation tells you whether it's spontaneous or not, because, and it bases it off of the enthalpy. So delta G could be the energy released from breaking the phosphate bond of ATP. Yes, that's exactly, yeah, definitely. Well, no. Delta H is that. Delta H is that. Delta G is just the chemical potential. So, well, you know what? Yes. The amount of energy that could be released into the surroundings. Yes. Okay, so yes, assuming you're correct. I had to think about that for a little bit. Yes. Okay, so let's do an example. All right, so let's look at this first. There's a lot of stuff going on. All right, here's some cases. And you don't have to memorize these cases, but it would be good to know based on the equation, you can figure them out. So here's what I'm gonna do. I'm going to paste the equation over here. It's too small. Okay, that's good. And we'll take a look at it. All right, so delta G will be negative, meaning it will be spontaneous. When delta H is negative and delta S is positive. That makes sense because you'll have a negative minus a positive, which means a negative minus something else makes it negative. And temperature's in Kelvin, so it's never positive. It's never negative. Why does that make sense? If it's exothermic, it's releasing energy and the molecules of it are getting more random. That's perfect. That is the perfect case scenario where something is spontaneous. Of course it wants to be spontaneous. Next one. It's spontaneous when delta H is negative and large and delta S is negative but small. That makes sense because delta H is going to be negative, meaning it's exothermic. So liquid water freezing into ice. And delta S is negative, but small. So when delta H is negative, for let's say water freezing into ice at low temperatures. Look, it's low temperature, right? It already says that. That's why, so we're minimizing this value. And this value is large negative. That's the way that delta G could be negative in that case. So you have the releasing of energy of these water molecules when they form this rigid ice structure. And that amount of energy lost to the surroundings is pretty large. But the delta S that is lost from the system is pretty small, and the delta S gained by the surroundings is larger than that. And also, it's at a low temperature. So that minimizes the T delta S value. Okay, so the next case is when delta G is negative, meaning it's spontaneous, when H is positive but small, and delta S is positive but large. So when basically the opposite. So you have a endothermic reaction that is still spontaneous, meaning its entropy must be a large gain of entropy. So that's when you have the evaporation of water molecules into vapor, right? Evaporation is a great example of that. So you have delta H, it's endothermic, but it's small, and this could be boiling also. And then delta S is going to be large because the amount of disorder you're gaining, going from liquid to gas is huge. And it's going to be positive for the system. That means delta G will be negative. Okay, and the next one, well, the only thing left is when something's not spontaneous. When delta H is positive and delta S is negative, meaning you're going from a positive, minus, and minus, meaning a positive plus a positive. So that's never going to be spontaneous, ever. And when delta G is at 0, there's no net energy, there's no energy movement really, and it's just, everything's at equilibrium, all good and dandy. So I would suggest for the example, or for the exam, for the final exam when you're going to see this, if you have this equation and you understand how it works, you will be able to answer any of these questions. If it asks you about, in which case is the thing spontaneous? So you think, all right, delta G spontaneous has to be negative. Now, which parameters make it negative? And then you just go through the list. So, or you go through the answer choices and see which one makes sense. So that's an alternative to memorizing all of these different scenarios, which I don't recommend doing. All right, so we'll go like we'll go like 10 more slides. All right, so free energy changes. All right, so if you have this reaction, right? This is we have N2 gas and H2 gas make 2 NH3. Okay. This is an equilibrium reaction. In the beginning of the reaction, before the reaction, and we're bringing back Q and K here. Remember that Q is less than K in the beginning, because you have most of the molecules are reactants, and then eventually they turn over to products, but then they might go too far. And then if you have just products, they will go down to reactants, and then the concentration changes or the rate of changes in the forward and the reverse reaction will be equal, making an equilibrium Q equals K. So Q is the reaction quotient, if we remember. So the idea here is that going from, if you're at either extreme, the reaction will be spontaneous in the direction that will get you to K, that will get Q equals to K, which we know. We've seen this before, that, okay, if Q, we can calculate Q, we can see that, all right, if Q is larger than K, the reaction will have to go in the reverse direction. If Q is smaller than K, the reaction will have to go in the forward direction. So we've seen this before, and it's just relating to spontaneity. And that process, by going forward and backwards, is spontaneous until it reaches equilibrium. Even when we use Le Chatelier's principle and we add or remove product or reactant. So here's examples of this Gibbs free energy, negative or positive. Here's a good chart representing all of it. You can look over that and really analyze it when you study for the final. a while from now, but it's basically everything we just talked about. All right, conceptual question. State which statement is true regarding the sublimation of dry ice. So sublimation of dry ice. First question should be, is it, well, since we're dealing with temperatures here. So, I mean, I would say go through the answer choices. I'll give you a second and then tell me what you think. Oh, sublimation, that's Chem 1. So Sebastian, it's okay. So sublimation, anybody want to tell me what sublimation is? And thank you for asking the question.
It's going from solid to gas while skipping the liquid phase, right?
Boom, exactly, solid to gas. But it's okay, it's a tough one of those phase transitions to remember. So good thing that you asked that question, because I'm sure a lot of you had the same question. So you're increasing your disorder, right? When you're going from a solid to a gas, drastically increasing it. So think about these and which one might be true. A, yes, A is true. Good, Sumi and Ahmad, good job. All right, so let's go through them. We'll look at B first, right? A is true, but we'll look at B. So sublimation of dry ice. Off the bat, is this process going to be exo or endothermic? It's going to be, well, H is positive, right? It's going to be endothermic because you're gaining energy. You're going from solid, low energy, to gas, high energy. So delta H is going to be positive. What that means is we can already cancel out half of our answers. So the answer is either A or D. Delta S of the system. Delta S, meaning you're going from solid, which is small or tightly packed, not much entropy, to gas, which is very fast particles, more disorder. That is clearly entropy equals positive. So the entropy will be positive. Exactly, less energy to more energy. Good. So less energy, yes, but less heat of reaction, more heat of reaction. And then we have the more disorder. So that means A is definitely true. But let's take a look at the rest of it. And because this one says delta H, delta S is negative, which is not true. And delta G is positive, meaning not spontaneous at low temperatures and negative at high temperatures. Now, if you think about that, delta H it's sublimation of solid CO2. And solid CO2, it's dry ice. So dry ice, what do you know about dry ice? It's very freaking cold, right? Negative 120 degrees Fahrenheit, I think. It's pretty cold. So at low temperatures, this is not going to happen spontaneously. At higher temperatures, you're going to have the spontaneous sublimation of CO2. So meaning delta G is going to be negative at high temperatures and positive at low temperatures. So that makes sense. Any questions on that one? No? Okay, cool. Okay, so we'll talk about standard states and then we'll take a break, or we'll talk about standard states. Okay, so standard conditions. Now, we can say what we're going to lead into is this idea of molar entropy. So molar entropy is, we can say there's a certain amount of joules per Kelvin mole that represents our molar entropy, or joules per mole Kelvin. It's whatever, same thing. But they say joules per mole Kelvin of a standard 1 mole of a substance, and usually at their standard state. So we can say for a gas, it's exactly 1 atm is a standard state. For a liquid, it's usually 25 Celsius. And for a solution, it's usually, or also for a solid, it's 25 Celsius and 1 atm. Then for a solution, it's usually 1 molar. These are standard conditions. Now, what we can say is that.
Can you go back for 1 second?
Yeah, sure.
Thank you.
Okay, good. Okay.
Yes, thank you.
Okay, cool. So we can say that we use this term, a perfect crystal. That's what this thing is. Basically means that it has, if you say that something has 0 Kelvin, meaning the molecules in the substance have 0 movement and no energy associated with them, that means your absolute entropy is 0, which is impossible. But we can say that, and that's what we call absolute entropy is 0. But we're not going to talk about that too much. What we are going to talk about is the standard molar entropy. So for 1 mole of substance at 25 degrees Celsius, based on its state, its allotrope, I'll talk about that word in a minute, its molecular complexity, its molar mass, and its degree of dissolution, we can tell which substance has a higher molar entropy. Okay, so let's just take one of those terms one at a time. Particular state, not like New Jersey, New York, but solid, liquid, gas. Out of the states, which one will have a higher entropy, molar entropy, solid, liquid, or gas? Which one? Good, gas. A particular allotrope. An allotrope is, here's the way I'll explain it. I'll explain it with an example. Diamond and graphite are allotropes. They are composed of exactly the same material, but a different three-dimensional structure. So out of the diamond to graphite, we talked about that example before, but I want to see who remembers. Which one will have a higher molar entropy? Good, graphite. So when you think diamond, it's hard, it's rigid. Graphite, more relaxed, more porous. It's not really porous, but it's brittle. So it's a pretty relaxed three-dimensional structure when compared to diamond. Then we say a molecular complexity. So you can think, are large molecules or small molecules going to have more entropy? Oh, so we have a little disagreement here. Okay, so generally it's larger molecules to an extent. So on the chemistry that we're talking about, it's going to be larger molecules have more, because the electron cloud, let's say in a benzene ring, compared to like H2, the electron cloud is going to be a lot larger here. There's going to be a lot more motion and commotion going on, a lot more entropy than just a single H2 molecule. But that also is determined by molar mass. So you can imagine if the complexity increases, the molar mass increases. And if the molar mass increases, you're going to have more space and more mass to move around. So our molar entropy will increase there too as you increase the mass. And then the degree of dissolution, we know what that means, right? That's chapter 18. We're talking about our insoluble salts. That's our silver chloride. So if that dissolves a little bit compared to our NaCl, which dissolves a lot, NaCl will have more entropy because AgCl is not going to dissolve too much. So the entropy change of NaCl solid to NaCl aqueous will be larger than AgCl solid to AgCl aqueous, because there's more motion going on. There's more of the water molecules ripping the NaCl apart. Okay, so now we're going to see this in action. So here we go. Here's a list of gases, solids, and liquids. And look at this. Look at water. Now water is right here. Water is 188.8. Its molar entropy as a gas. As a liquid, it's 70, and as a solid, it doesn't say. Are there any that say for everything? I don't think so. Okay, well, you get the point. It decreases. Not the best chart. I chose a better chart, but okay. And then here's for water. Here's the gas one. So here's liquid and gas. Why don't I have it for solid? But okay, so for solid, it's probably less. There's definitely less. But for gas, it's going to be larger. For liquid, it's going to be less. Molar mass. The entropy increases with molar mass, going from these noble gases, helium to neon to argon. The entropy slightly increases. It's not going to be too much of a factor. I would say the biggest factor is going to be your state. Because look, you're having almost a 3 times increase going from liquid to gas. Here, if you have an increase in molar mass, it'll be like helium to xenon. That is like a times what helium's 4, and xenon is what, like 100 in the 100. So it's at least a 20-fold difference, but the enthalpy or the entropy difference is less than 40. It's about 40 units. So it's not too big of a deal. And then you have the allotrope difference, and that matters. It depends on which substance you're talking about. But diamond to graphite, the entropy, the molar entropy increases by about a little bit more than 2-fold. Molecular complexity, the molar, so here's, we use this example down here. Carbon monoxide and ethylene. Ethylene is more molecularly complex. It has more atoms, but they're both about the same molar mass. Yet, ethylene has a higher molar entropy because there's more, and here's the way they describe it, is more energy states are available, allowing more dispersion of energy. So basically, the electrons, which are bumping all around, have more places to move, which then dissipates more energy into the environment when ethylene reacts with something. So it's just larger, and there's a lot of, in terms of surface area and energy dispersion. And here's an example of that. So like all these molecules, even like ethylene, every bond is vibrating and rotating, or not every bond, not the double bond, but the single bonds are all rotating. That creates some entropy. So if you want to look at it here, you have translational motion, you have the bonds sometimes rotate, and the bonds vibrate back and forth. So the more complex your molecule is, the more of that vibrational energy is going on. And then if you have, here's states, solid to aqueous, obviously solids have, dissolved solids, meaning aqueous, have a larger entropy. Okay, so we'll do this one and then we'll probably call it a day and then do the rest next week after the exam. All right, so arrange these gases in order of increasing standard molar entropies. So SO3, Kr, and Cl2. So what do we think? Ding, 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 got an answer. A, and A. Yes, the answer is A. Good, because krypton is 1 element. Chlorine is 1 atom. Chlorine is 2 atoms. And SO3 is 4 atoms, and it's a bigger structure. You got a lot going on. That's the scientific explanation of it. You have a lot going on. Okay, so what we're going to learn next week is we're going to talk about how to calculate Gibbs free energy of a reaction. And it's very simple. We've learned this already in the past. And yes, Sumi, the molar mass difference is not as important as the complexity of the molecule, because with more bonds you have, the more vibrations, the more rotations, the more translations. There's a lot of things going on. There's more that can happen, more entropic differences.